Hello, good day. Today we're having the topic Euclidean Geometry, but we're just doing the summary of this topic. And I hope you are good. And if you are ready, take your book, take your pen or your pencil. Let's get to work. Before we go any further, are you able to do this? Can you solve this question? What about this? What about this one? Do you have any clue how you can solve this? If you're having a bit of a clue, then stay tuned. Let's see how it will turn out, right? But believe you me, no matter your situation right now, because some people they hate Euclidean geometry, but no matter the situation, after today, after watching this, you'll be able to solve any question, even this one. You'll be able to solve this, right? So just get your pen, your pencil, and your book. Let's start. So don't mind the flu. I'm having a bit of flu, but don't mind that. So to understand Euclidean geometry, obviously I'll start from the basics, from the primary level or grade 8 level geometry, right? So let's see how it goes. So this Euclidean geometry is more like playing a game. Once you know the rules of this game, you enjoy playing it and you enjoy solving any questions, right? So I'll start from the lines or the dot or whatsoever from the previous work. So let's start here. So since this is the revision, I won't go too much into details, but I'm sure you are aware of this and I'm sure you have seen this before, right? So this is a straight line. So we know that angles on a straight line, they always give us 180 degrees, right? So our angle A plus our angle B is equals to 180, and the reason being is angles on a straight line. So angles on a straight line always gives us 180. And we can also move on. We also know that if we're having this situation here, when it is shown like this, it means that this is 90 degrees. So if we're having angles there, it means that our A plus our B should always give us 90 degrees, and the reason being it is a right angle. So all right angles, they give us 90 degrees, right? So now we can move on to a bit complicated but yet easy, right? We also know that if we're having two lines like this intersecting each other, we know that this angle here, it is also the same as that angle. So it means that our A is equals to our B. And the reason being, these are called vertically opposite. You can see how they are, right? So vertical opposite angles. So these are vertical opposite angles. So why am I teaching you these simple things? Why am I showing you this? Because whenever we apply anything in Euclidean geometry, the basics are important, right? So let's go on to the next. So we also know that if we're having a point like this and we're having angles around this point, so maybe our A, B, C and D there, we know that our A plus our B plus our C plus our D, if we add all the angles that are on a point, that are around a point, they give us 360 degrees. And the reason being angles on a point. So some like to use other reasoning like revolution. So some use revolution, but if you can just say angles on a point, you are still perfect, right? So now we talked about these 4 reasons. Now let's escalate a bit, right, so that we can pace up. So working with parallel lines can be a bit complex, but yet easy, right? So whenever you're given parallel lines, there are 3 things to look for, right? But in Euclidean geometry, we don't just assume, right? So if you're given lines like this, they don't mean anything up until they tell you that they are parallel or they show you something like this, then now they are parallel. So it means that this and this, they are parallel. So it means that AB is parallel to CD, like that, right? So let's see. So if we are having angles like S, T, U, V, W, X, Y, Z, so it means that there are three things that you must know at instant if you're given situations like this. So we look for corresponding angles. So what are corresponding angles? Corresponding angles are angles on the same side of the parallel lines. So our angle S is on the same side with W. So our S being equals to W, and our U the same as Y. So our U is equals to Y, and also our T is equals to our X. So T being equals to X, and also our V equals to Z. So our V is equals to Z. So these are corresponding angles. So we also have what we call alternative angles. So alternatives are the ones that forms a Z. So we can draw a Z like this. So we can see that our U is equals to our X. So U is equals to X. And also our V is equals to our W. So our V is equals to W. Right? So these are alternative angles. And we can also have co-interior angles. So co-interior angles are the ones that are found inside. So this and this, they're inside, so they are co-interior. So it means that our V plus our X give us 180. So co-interior angles are supplementary. So what does supplementary mean? So supplementary is when you are adding those angles and they give you 180. We call that supplementary. And we also have another term that is called complementary. So when you add angles and they give you 90 degrees. So also here, our U plus our W, these they're inside, so they are co-interior. So our U plus our W give us 180 as well. So this is the reason we use here, and this is the reason we use here, and this is the reason we use here, right? Because we're having parallel lines. Okay. So triangles are very, very important when you're dealing with Euclidean geometry, because we can be working in circles, but the bigger part is the triangle. Triangles are very, very important, and I will advise you something after this lesson, right? So obviously we know that our A plus our B plus our C is equals to 180 degrees, and the reason being is a sum of angles in a triangle, right? So these are the property that you are going to be using, right? And if I extend, maybe here, if I can just extend this line here and extend it up to here, so here still have our C and our D, and maybe we can have 1 and C2. So now we know that this angle C2 here, that is a external on the extended line, it is the same as this angle plus this angle. So our angle C2 is equals to our angle A plus our angle B, right? And we say this is the exterior angle of a triangle being equals to sum of opposite interior angles. So the exterior angle of a triangle, this exterior angle, is equal to the sum of the opposite interior angle. So this plus this give us this. no matter the situation, if we extend also here, to mean that this will be equal to this and this. If we extend there also, it means that this will be equal to this plus that. So still fine like that, right? So now I want us to talk about this special type of a triangle. The drawing doesn't matter. Okay, so I want to talk about this special type of a triangle, the isosceles triangle with two sides equal. So most of the times we work around this in Euclidean geometry, right? So we know that in this case our B is equal to our angle C. So this angle will be equal to this because these sides are equal. So we say angles opposite equal sides are equal. So these angles that are always opposite equal sides, they're equal. And in some other point they can reverse this situation, and we can be having something like the sides now, I mean the angles now being equal. So if we are having the angles being equal, it would therefore mean that AB is equal to AC, because sides opposite equal, angles are equal, something like that. So I think that's what I want to say on isosceles triangle. So you must always remember this, right? So I can just explain what is congruency and what is similarity, then we can move to the summary of the circles, right? So similarity, always when we're proving similarity on the lower level cases, we just prove that all three angles are equal on a what? On a triangle, right? So the other part, I'll deal with it in the grade 12 part, right? When we're talking about the triangles, right? The similarity. And then in congruency, if you want to prove that triangles are congruent, we either prove that two sides plus one angle are equal, or we can prove that two angles and a side, or we can rather prove that three sides are equal, right? And if we talk about three angles, then it will be similarity, right? So we don't talk about that when you're dealing with congruency, right? So congruency, these are the reasons that we have to prove, or these are the things that we have to prove in two different triangles, then those triangles becomes congruent, right? So congruency is more about things that are the same in everything. They are actually equal in everything, right? But when we're talking about similarity, similarity can be this triangle and this triangle. This triangle is bigger than this, but if the angles are equal, it means that they are similar, right? It's more like saying identical twins are congruent because they are the same on everything. And then siblings, they can be similar but not congruent because they are not the same on everything, right? So now let's do the summary of the circle geometry. So I'll just show a few things about the circle geometry, and then I'll just run over the theorems that we done in grade 11, right? The summary of those and how to use them, right? So circle geometry, right? So let's just go over everything a bit at a time. So obviously we have the center there, right? So any line from the center to the circumference, we'll call that the radius. So we can have like this. So we know that all the radius are always equal, right? So this line will be obviously equal to this line, and this, if we join like that, it means that our A, B is a diameter, right? So this AB is a diameter. So if we have any line that is not passing through the center like this, then this line is a chord. So this is a chord CD. You can have a chord anywhere, right? Even here, if I draw something like this, CF, it is also a chord. So this is a chord because it is not passing through the center, right? And we can have a line passing inside the circle, not passing through the center like that. That is a secant. So that line is a secant. And we also have something that is called a tangent. So a tangent only touches the circle at only one point, just like this. It only touched this circle at R. It doesn't go inside, it just passes outside like that, right? Touching the circle at only one point. So maybe this Y, maybe. So this becomes our tangent. I'm sure by now you already know these these definitions, right? And you know how to use them, right? And again, so here we're having a chord CD. So whenever you're having a chord, you have an arc. So this is an arc, right? We're having a minor arc and the major arc. So this is the minor arc and this is the major arc. So now let's talk about all the other theorems and how we can apply them, right? Yes, and I'll also be showing you the tricks that you have to be aware of every time you see the words written there for you, right? We have center chord theorem. Center chord theorem. So center chord theorem says a line drawn from the center bisecting the chord. So we can see that AB is equals to BC. So this line cutted this AC into two equal parts. So whenever that happens, we know that OB becomes perpendicular to AC. And the reason being, it is center chord theorem. So again, they can give you that vice versa, right? They can also give you this as this line, and they say OB is perpendicular to AC. But you can see that this line is from the center and this is our chord. So if this is our chord and this is perpendicular to that, we can conclude that therefore our AB is equals to our BC. And the reason being, again, it is center chord theorem. So every time that they give you that you're having a center, so check if you're having a chord that is being bisected or the chord that is perpendicular to the what? To the line drawn from the center. So that is trick number one that you must always check. Whenever that they give you that you're having a center, right? And you're having a line drawn from the center going to a chord. So you must check for that. So let's go on to our other theorem. So now angle at center is equal to 2 times angle at circumference. So whenever you're having or you're given that there's an angle at the center and angle at the circumference, always check one thing. Are these two angles given by the same chord? Because you can see that we're having a chord AB. So if we follow the chord AB, it gives us our angle O1. And if we follow this, again AB, it gives us angle C. So we can now say angle at the center is equal to 2 times angle at the circumference. So it means that our O1 is equal to 2 times our angle C, like that, right? And most students often do a mistake of this. So let's just see. So we can be having our center here as O, right? And we can be having an angle like this, and we can also have maybe C there giving us the angle at the circumference like this. So this angle, this one, it will never be 2 times, it will never be half of this. There's no relationship between this angle and this angle because they are not given by the same chord. So chord AB gave us O, but now this angle, it is given by the chord CB. So that will never be the same. that will never be the case. And another common mistake that I've noticed in years is that we can have something like this and we can have something like this going on. So this angle will never be 2 times this angle, because this angle is not at the circumference. So that will never work, right? So always check out for these two mistakes that I told you about just now, right? So that you can be able to locate exactly where this reasoning work, right? Yes. And now if we're having AB, C inside and AB as our diameter, now we can now say now our angle C now becomes 90 degrees. So this angle becomes 90 degrees because it was subtended by a diameter, right? So we can just say angle subtended by a diameter, or we can say angle in semicircle, like that. So this is one and the same thing, right? But we just have to know that this angle becomes 90 degrees. So now if we're having a situation like this, we can see that our chord AB, or our chord AB is subtending angle C and angle D there. So we can quickly say our angle C is equal to our angle D, because these are angles in same segment, like that, or angles subtended by the same chord. The chord that we're talking about, it is AB. So if we follow AB, it will give us D there, and if you also follow AB, it will give us C there. So those are angles in the same segment and they should be equal. And again, don't make a mistake of if you're having maybe a situation like this. This angle will never be equal to this angle. This will never be the same. Why? Because this angle is subtended by another chord and this angle is subtended by the other chord. But now if we can have something like this, it means that this angle now can be equal to this angle because they're subtended by the same chord, right? Yes. And again, this reasoning gives also birth to this. Some people there don't know this, but let me just give you this for free. So inside the same circle, if you're having equal chords, so this chord is equal to this chord, they always subtend equal angles. So it means that our C again becomes equal to our D. And the reason being is because equal chords subtends equal angles. So equal chords will always subtend equal angles, just like that, right? So now let's move to a cyclic chord situation, right? So a cyclic chord is characterized by these things. So the first one we just talked about is angles in same segment. So if you can have angles in the same segment equal, that shape is a cyclic chord. Or if we are given that a cyclic chord, we can always say angles in the same segment, they are equal. And the other thing, it is this shape here. I'm sorry for the shape, guys. Maybe something like this. So this is our cyclic chord A, B, C, D. So we also know that opposite angles of a cyclic chord are supplementary. So it means that our B plus our D is equals to 180, right? Because opposite angles of cyclic chord are supplementary. We already talked what is supplementary, right? And also it will mean that our A plus our C, because this C is opposite to this A, so also equals to 180 degrees for the same reason, right? And also, if we can extend a line outside here, so this angle is called the exterior angle of a cyclic quad. So angle D2 there, so this is 2 and this is 1, will be the same as our angle B. So this extended angle outside here, it will always be equal to the opposite interior, right? So we can just write that down as exterior angle of a cyclic quad is equal to the opposite interior angle. So the exterior angle will always be equal to the opposite interior angle. So these three things are the ones that makes a shape a cyclic quad, or if they are there, it means that the shape it is a cyclic quad. Or if a shape is a cyclic quad, then we know that we can look for these three things, right? So this is another trick. Whenever that they give you that this is a cyclic quad, always check for these three things. And again, if they say prove that this shape is a cyclic quad, then prove any of these three, right? Let's move. So let's talk about the tangent. So one thing that you must know is a tangent is always perpendicular to the radius or the diameter, right? So tangent is perpendicular to radius or diameter, right? So we can see that OB is perpendicular to AC because tangent is perpendicular to the radius always, right? So that's one thing. If you're given that you're having a tangent, you check for this. And the other thing that you check for, it is this. This is a bit complex, but just check. Whenever that you're given that a line is a tangent, and you can see a triangle that is drawn from that point of contact inside the circle like this, just know that this angle here between the tangent and a chord, can you see that we're having a chord TA there? So this angle that is given here, it will always be equal to, if we follow that line, so we'll get this. So this angle will always be equal to this one, and this is the tan chord theorem. So that's the tan chord theorem. And also this angle that is here, if you can check, this angle is between this chord. Let me use a different color maybe. If you are having this situation here, so this chord BT, it is making up this angle. So we just follow the lines BT to see where they are going, and they are going here at here. So it always mean that this angle is equal to that angle on tan chord theorem. So that's tan chord theorem. So the last one that we can have on tangents, so this is the second situation that you have to check for whenever you are given tangents. We can also have, if we are having two tangents from the same point outside the circle. So these two tangents from the same point outside the circle, they will always be equal from the point of contact. So like this, so this will always be equal to that. So always check for this as well when you are given two tangents, right, at the same circle. So we can say tangents from same point outside the circle are equal, right? So it means that our AE will be equal to our TE, because tangents from the same point outside the circle are always equal, right? So now that you are done with the whole summary of Euclidean geometry up to so far, I'll just give out some questions so that we can try to work on this, right? So we just take it a step at a time, no rush. And then just because of the length of the video, I'll just do another one focusing on the grade 12 work. But when it comes to grade 12 work, I'll just put in the details a bit so that it sinks in, right? I wish you guys good luck. But before I can go, obviously, let's solve some questions.